end of the alpha apparatus. The antiprotons come from the antiproton decelerator from that direction. And we trap them inside of this magnet. This is a large superconducting magnet that holds the atom trap and the charged particle trap. So we trap antiprotons and positrons in this magnet. We put them together to make antihydrogen, which is then trapped inside the atom trap. Then we shine the radiation on it, the microwaves, and cause it to escape. And when it escapes, we detect that it annihilates. You get this microscopic explosion when antimatter hits matter, and we're very good at detecting that. So that's why we're able to measure on just one atom. So what we're doing now is actually looking into antimatter for the first time, an antimatter atom. We're actually studying it the way that atomic physicists have been studying hydrogen and helium and all the other atoms in the periodic chart. We're actually addressing an antimatter atom in the same way. We're starting to learn how to do that. And that's a huge step forward for us because we've never been able to do that before. So this step of last year of storing things for 1,000 seconds, that's what allows us to do this. We need some time to interact with this trapped atom. So we demonstrated we could do that. In fact, in this experiment, we only used 240 seconds, and still we have a very strong signal that we can identify. So these things have built up. Trap antihydrogen, store it for some time, shine some light on it. In this case, it's not light, it's microwaves. Light is the next step. We'd like to shine lasers to continue the spectroscopic investigation of antimatter. That's what this is about, looking inside the structure of the anti-world. This step is very important for a few reasons. Again, we want to compare the structure of antihydrogen with that of hydrogen. That's the whole point of our physics program. So this is the first measurement of the internal structure of antihydrogen, where we've actually used radiation to see what's going on inside this antimatter atom. The other important thing about this measurement is that it demonstrates that you can actually measure with very few atoms of antimatter. If you have matter, you can just buy it. You can get your hydrogen from a gas bottle. But we have to produce these antiatoms. They're very rare. It's difficult to make them, difficult to trap them. So one of the big questions has always been, will you ever have enough to be able to make a measurement? And now we've demonstrated that even with one atom trapped at a time, on the average, we can probe the internal structure of the antihydrogen atom. So we're very excited about that. We now know that in the future, we can make experiments, we can design experiments that will succeed, or have a good chance of succeeding. That's a very, very important step for our community to be able to say, all right, you're actually measuring something now after more than 20 years of efforts to just learn how to get this far. So for us, it's a huge relief that we're actually starting to make measurements on antihydrogen. So what's the next step here? The idea now is we know we can measure something. The whole idea is to compare to hydrogen. And to do that, you need to measure more accurately. Okay, so in the next 5 to 10 years, what we'll be doing is improving these measurements to make them more and more precise. Hydrogen is the thing in the universe that we understand the best of all the atoms. So in order to look for a difference between hydrogen and antihydrogen, you need to be able to keep measuring more and more accurately. So that's what will happen. In fact, we're building a new machine now called ALPHA2, which will attempt to do that, both with microwaves and with lasers. So we have a double program now. In the future, the idea is just to make this measurement more precisely. Several measurements. There isn't just one that you can do. Anything we can try, we'll try. The idea is that since you can hold it for so long, you know you can measure. So that's what we're doing now.
This is the central portion of the alpha apparatus spinning into view. You're looking at the silicon annihilation detector, which is the 3 layers of segmented things. They'll peel back in a second so you can see what's inside. The tube sticking out either end is the inner portion of the cryostat, the liquid helium vessel for the magnets. Now you see the superconducting magnets that make up the atom trap. There are an octopole and 2 mirror coils. These are what actually trap the antihydrogen atoms when they're produced. They produce very strong magnetic fields that grow from the center of the apparatus. The arrows indicate the direction of the current in the superconducting magnet coils. It's about 1,000 amperes for the octopole and about 700 in each mirror coil. Now those will peel back. You'll see the vacuum chamber open up. The yellow cylinders are the electrodes for the pending trap. These are used to help trap the charged particles. The whole device sits in a superconducting magnet that gives a constant field of about 1 Tesla and holds the particles transversely to the axis. These are the potentials in red applied by the electrodes. You see a cloud of positrons in green in the center and a cloud of antiprotons that's being driven into the positron cloud to form the antihydrogen. These particles obviously have opposite charges, so they're in different curvature potentials. So now the antiprotons go into the positron cloud, hopefully very slowly so that you can make cold antihydrogen. 2 positrons scatter in the field of the antiproton and produce the antihydrogen atom. So that's it, antihydrogen, 1 antiproton with a negative charge, 1 anti-electron or positron with a positive charge. So if that antihydrogen is formed and it's slow enough, it will stay in this magnetic bathtub. You can see it at the bottom. This is the potential that's used to hold the antihydrogen atom. So if it's less than 0.5 Kelvin above absolute zero, it'll stay there. Then if we want to see if it was there, we release it quickly. That's what's happened here. We've turned off the magnets. The antiproton from the antihydrogen annihilates, produces high-energy charged particles which come out and are registered by the silicon detector. So we can recreate the position at which the thing annihilated. That's how you know you had antihydrogen. Now here's the experiment we've just done. The antihydrogen is trapped because it's slightly magnetic, and that's indicated by the little arrow flying around with the atom. We shine microwaves on that little magnet and cause it to flip into the other direction. It'll happen more slowly here. You see the magnetic moment, sort of like a compass needle in the antihydrogen atom, has to point in one direction for it to be trapped. The microwave radiation flips that magnetic direction, and that means that the atom is untrapped and comes out. And that's what happens. You detect the annihilation. You need to have the frequencies of the microwaves exactly correct. And that's what's resonant about this experiment. So if you tune it correctly, you force the antihydrogen to come out, and you can detect it. That's how you know you've done a resonant interaction.